All right, welcome back, guys. In this little video, I'm going to be talking about the SAC redemption task that we're doing um, to do with developing splines. So I've already shown you a little video that introduces the concept of a spline, and in this video, I'm just going to basically demonstrate what you have to do for the SAC. In the SAC, I'm going to give you 5 points, or like a series of points. Might be more than 5. I can't quite remember, but let's suppose we have 5 points, and we need to figure out what would the spline or the Catmull-Rom spline look like for these 5 control points. Now, we see here the little definition of a spline that you saw in that video. It's cubic splines, so it's a piecewise function with cubics of restricted domain where the gradient in each of the knots, now when it says knot here, that's basically the point where two piecewise functions are going to connect to one another. At that knot, the gradient is equal between the two line segments that make it up. So in other words, it's smooth and continuous across its whole domain, and the endpoints have a gradient of 0. So the process that you're going to go through to do this is basically step 1. We're going to try and come up with linear equations that connect these 5 points. So what I'm going to do to start off with is I'm just going to basically approximate where these are. If you were using graph paper, you would create a more accurate drawing than this. But let's say the drawing for this diagram looks something like this. I'm just going to see if I can locate where all of these points are to start off with. So this point here, 0, 4, it's going to be somewhere here. So let's say that that is 0, 4. 110 is going to be somewhere up here. So that's 110. And then we have 2, negative 3. So that might be down here somewhere. So 2, negative 3, let's say that's there. 3, 5, that is going to be, let's say here. So 3, 5, and lastly 4, 8 is going to be about here. Okay, so we've got our points labeled there. What we want to do to start off with is to find the piecewise defined function that's comprised of a bunch of linear equations. So we want to find basically piecewise function defined of a bunch of linear lines that look like this. And I know this is not the most accurate diagram, but let's see if we can use this as like a basis, and then we might get a bit more accurate in the future. So what will this function here look like? So let's call that first function, let's say it's f1 of x, okay? Now, we need to find the equations of these linear lines that separate or that connect these points here. So the way that we're going to do that is by solving a system of simultaneous equations defined based on the linear equation. So we are trying to find a linear equation. So I'm going to go edit, action command define, and I'm going to define f of x is equal to a times x plus b. So, or mx plus c, whatever you want to do. And we want to find what a and b are in this equation. So we're going to use our system of simultaneous equations. I want the line, maybe this first segment here. So this first one right here. I want that line there. So the way that we're going to find this one is by substituting in when x is equal to 0, y is equal to 4, and when x is equal to 1, y is equal to 10. So the way that we could type that in on the CAS calculator screen just over here is I can say f with an input of 0 is equal to 4, and f with an input of 1 is equal to 10. And I want to find what is a and b equal to. And it tells me that a is equal to 6 and b is equal to 4. So this can be our first equation in our piecewise function. So what this tells us is that this first equation is 6x plus 4, and it's defined like this from x greater than or equal to 0 up to 1. So this is this first part of the piecewise function. So that first segment from 0 to 1 is given by that equation right there. All right, so let's continue with this. So now we want to define when f is equal to 1, we want y is equal to 10, and for this second line, when f is equal to 2, y is equal to negative 3. So we can do the same thing as before, sub in these 2 points to find what the equation looks like. So we put in these 2 points, and this time we're going to solve for a and b, and it's going to give us a different answer. So this time it's giving us a is equal to negative 13, so this is negative 13x plus 23. And once again, we're going from x is equal to 1, x is equal to 1 up into x is equal to 2. Once again, we can type this in once more and figure out the spline between the next two curves. So this is from f3 is equal to, when x equals 3, y is equal to 5. And we're currently looking at this line here, by the way. So for this one, we've got 1 point here, 1 point here. So we're going to use those 2 points. So when x is equal to 3, y is equal to 5. When x is equal to 2, y is equal to -3. And once again, we're solving for a and b. That tells us that this equation has, this line has the equation 8x minus 19. And once again, that's from x is equal to 2 right up to x is equal to 3. Okay, final line that we have to define is this one right here. And once again, we can do that in the same way. So when x is equal to 4, y is equal to 8. When x is equal to 3, y is equal to 5. Solve for a and b. Okay, so now we have developed our system of equations for these points. So minus 4 from x is equal to 3 up to x is equal to 4. Now, as we can see, I've defined now this pink little graph of lines, and this is going to be kind of the basis that we use for our splines now. Now, the difference between the lines and the splines is the splines, we want them to be smooth and continuous. So you can see that an issue with this current function, this f1 function that we've defined here, is that it's actually not smooth. So although it is continuous, at each of these endpoints, for example, this first line here, if I sub in 1 into that equation, I'm going to get 6 plus 4, which is equal to 10. And if I substitute 1 into this second equation here, I'm going to get -13 plus 23, which is also equal to 10. So at each of these endpoints, so that's this point here, 110, so it lies on that curve. At each of these endpoints, we have continuity, so the lines are continuous, but they are not smooth. So we're going to try and fix that. So we're going to set up our splines. So we're going to use a different color for this. So maybe we can use green. And the way that splines work is it says that the gradient at the endpoints is equal to 0. So it's going to be like a cubic function. Gradient at these two endpoints here is going to be equal to 0. And then we want the knots at each of the control points to be something. So it needs to be the same for the two functions. So we're trying to create a smooth sort of function. So it's going to need to go up like this, and then it's going to reach a value, and it's going to go down here, reach a value, go up here like that, and it needs to be a smooth sort of curve. So we're going to work point by point for this one. So let's now consider, this is F2, and this is the one that is the spline. So for the first segment, from this part where we go from 0, 4 up to 110, we want our equation to meet the following criteria. In fact, we'll do it down here. So each of these little line segments, each segment is a cubic of the form y equals ax cubed plus bx squared plus cx plus d. Okay, so let's consider this first cubic. So that first cubic needs to satisfy the following conditions. If we call that, say, I don't know, I already called that f1x, so let's call this one spline 1. I don't know, spline 1. So spline 1 has to satisfy the following criteria. Spline 1 must be, when we have x equals to 0, we need to have y is equal to 4, right? So this point here lies on the spline. Similarly, when x is equal to 1, y needs to be equal to 10. So these are the conditions that we had before for the linear line. But also, we're now added that the gradients at the endpoint is equal to 0. So the gradient here at this endpoint, when x is equal to 0, the gradient is equal to 0. So that's the derivative, I should say. So the derivative when x equals 0 is 0. And then finally, what about one more piece of information? Because we're dealing with a cubic, So it has four unknowns, A, B, C, D here. We're trying to find those four unknowns, so we need one more piece of information. And what we use for that is actually the gradients of the two lines that we had at the start. So if we consider these two purple lines here, what we want is for this green line is going to have a gradient at this point right here, which is the average of the two gradients on either side of it. So if we consider the two pink lines on either side of this spline here, that's this one here and this one here. The gradient of this one, of the first line, is 6, and the gradient of the second line is -13. So we want the gradients at the endpoint. So gradients at 110, we want that to be the average of 6 and -13, which are the two gradients of the lines on either side. So what we're going to do is we're going to go 6 plus -13, and then simply just divide that by 2 to work out the average of those 2 points. So 6 plus -13, that's equal to -7. -7 divided by 2, that is -3.5. Yep, that seems to check out. So -3.5 is the gradient, and that's how we're going to define it. So this is our final condition. When x is equal to 1, y is equal to, when x is equal to 1, the gradient is -3.5. And let's put this in as our conditions. So to do this, we're going to first define our function. So we can go action, commands, define the function. We'll call this s. S of x is going to be equal to a of x squared plus b times x squared plus c times x plus d. Okay, now we also need the derivative of this, so we can define the derivative. So dy dx is going to be equal to 3ax squared plus 2bx plus c. So we should be able to take the derivative of this using the power rule. So the derivative function is going to be equal to 3 times a times x squared plus 2 times b times x plus c. Okay, we've now got our two functions. Now let's put in the various functions here. So we're going to set up what we have here. So we have each of these conditions need to be met. So we just these ones that I've written over here to the left. So s of 0 must be equal to 4. S of 1 must be equal to 10. That's these 2 points here on the graph. And also the derivative when x equals 0 must be equal to 0 because that's a condition. And then finally, the derivative when x equals 1 must be equal to -3.5. And we're solving for a, b, c, and d. So it says no solution. So I must have made a mistake somewhere there. Let's see if we can work that out. So we've got those conditions. The derivative function, is that all correct? So that's ax cubed plus bx squared plus cx plus d. 3ax squared plus 2bx plus c. Yeah, that's the derivative function. When x equals 0, y equals 4. When x equals 1, y equals 10. Yep. When x equals 0, y equals 0. Maybe we need to make sure we've cleared all the variables and try that again. A, B, C, D. So we've taken the average of the two neighboring graphs there. We've got 4 conditions. Not doubling up on anything. That should be fine. Why is that no solutions? Ax cubed plus bx squared plus cx plus d. This is another one of those cases where I've defined d. Okay, so you've got to be careful about this. I think this has happened before in the past. I've defined d here as being a constant, and then because the function has the same name as that constant, that's caused the issue. So let's avoid that mistake. I'm going to call this second function g rather than d. So it's creating a bit of an issue there, I think. So now if I clear all the variables again and then hit enter, now it gives me an answer. Okay, so be careful with that. That could just as easily happen to you. So I guess it's, again, probably good that it happens here. We can't name the function the same thing as one of the variables. So we've now created our first spline, and I'm going to put this in as my overall function SX. So the function SX, which is the spline of this graph, is now going to have the equation negative 31 over 2x cubed plus 43 over 2x squared. There's 0 is the component for x, and then plus d, and this, sorry, plus 4, and this spline is defined from x equals 0 up to x equals 1. Let's do another one. So that's the first spline, getting to here. Now we need to consider the second spline, so this second segment from here to here. Now it's going to be very similar to that first one, and now hopefully you can see that things will be a little bit quicker. The only thing that we need to work out before we do that is what is the gradient at this point supposed to be. So gradient at 2, negative 3. To work out what that gradient is supposed to be, we go back to our linear graph here and we consider the two lines on either side. So that's this line and this line. So the first line there has negative 13 as its gradient. The second one has 8 as its gradient. So therefore the average of those two gradients is going to be negative 13 plus so let's go back here. So negative 13 plus 8 divided by 2, that is negative 2.5. So negative 2.5 is the required gradient at this point right here. And that's actually all we need to sort out what this function will be. So we can just use the same functions that we had before. They're still stored in the system. So when s is equal to 1, y is equal to 10. So when x is equal to 1, y is equal to 10. When x is equal to 2, y is equal to negative 3. So that's the 2 points that lie in the curve. With regards to the gradient, we know that the gradient when x equals 1 needs to be negative 3.5. So this needs to be the same as the previous spline. So that will be when gradient is 0, when x equals 0, the gradient is negative 3.5. And that's when x equals 1, the gradient is 3.5. And when x equals 2, which is at this second point here, this one, the gradient, as we just worked out, needs to be equal to negative 2.5. And once again, we're solving for A, B, C, and D. Hit enter, and it gives us some big numbers. That's fine. We'll just type them in. So we've got 20x cubed minus 179 over 2x squared plus 231 over 2x minus 36, and that's going to be defined from x equals 1 up to x equals 2. All right, so that is up to here now. So now let's move on to the next one. So in the exact same way, we need to work out what's the gradient at this point going to be. So gradient here at 1, 5. So the gradient at 1, 5, again, it's going to be the average of the two lines next to it. So this line here had a gradient of 8. This line had a gradient of 3. 8 plus 3 divided by 2 is equal to 11 divided by 2, which is 5.5. So that's the one that we're going to use for this next function. So we jump back across to our CAS calculator. So we can now see that the gradient at that first point, so we'll just type in our known values. So our system is first point, this one over here. At that point, we need to have the s of 2 needs to be equal to negative 3. S of 3 needs to be equal to 5. So those are the 2 points that lie in the curve. Then with regards to their gradients, the gradient at 2 must be equal to negative 2.5, and the gradient at 3 must be equal to 5. And once again, we solve A, B, C, D, gives us the answer like so. And I'm just going to write that in over here. So that's negative 27 over 2x cubed minus 105x squared minus 521 over 2x plus 20, I believe that is 206. Okay, from x equals 2 up to x equals 3. All right, very last spline. Once again, we're going to use all of these conditions. So for this last one, we need to consider the two endpoints for this last segment from here to here. So this last segment here. At the endpoints, we have x is equal to 3, y is equal to 5. When x is equal to 4, y is equal to 8. So those are the values, this point and this point. And then with regards to their gradients, if we consider the gradient at this point here, we found that that's equal to 5.5. So, sorry, I think I mistyped that in the last line. So the gradient there should have been 5.5. So that leads to an error from before. So that was wrong just before. I'll just fix that up because I think I forgot to type that in properly. Yeah, so this is what I should have said. And I'll just delete that previous line over here. Sorry about that. So yeah, fixing that up because the gradient was wrong at that endpoint. We have negative 13x cubed plus 203 over 2x squared minus 505 over 2x plus 200 for 2 up to 3. Okay, finally, let's find that last spline. So for this last spline, we have the following 4 conditions. So we have when x is equal to 3, y is equal to 5. When x is equal to 4, y is equal to 8. The gradient at that midpoint is 5.5. So when x equals 3, the gradient is 5.5. And what's the gradient at the endpoints? Should be equal to 0. So remember, splines are defined such that the endpoints at the gradient must be equal to 0. So that's a given from the start. So A, B, C, D, and we can find the following values. And that fully defines our spline. Plus 5 over 2x squared minus 4x minus 16 for 3 up to 4. And now all we have to do is just graph that and double check that it does in fact produce something that looks a little bit like this. So what we could then do is then type these into the CAS calculator, graph it real nice, and just double check that we have created a smooth and continuous function. But that's just about it. So that shows you how to create splines using this method. And this is essentially what you have to do for the SAC. So what I would recommend if you wanted to come up with what is a way that I can prepare for this SAC, I think all you have to do is maybe just practice this method. You can just come up with 5 random coordinates. So I just came up with these points here randomly. 0, 1, 2, 3, 4, 1, 2, 3, 4. And then a bunch of random y values. You can produce similar points to this, and then you need to double check that it does actually create a smooth and continuous function just to check you're working. So you can do that on the CAS calculator, just on the graphing screen. So for example, to type in this first one, just to get you started on how you might check this, we could go negative 31 over 2 x cubed plus 43 over 2 x squared plus 4. And the way that we specify the domain, which is what you have to do here, is give this vertical line a click, and then we can say from 0 x up to 1, and then if you click this button here, it will graph that one for you. And as we can see, that does produce, and if I zoom out a little bit, there we go. If you look at those 2 endpoints, it's kind of hard to tell looking at it, but it certainly does look like we're starting at 0, 4, and we're going up to 110. Let me just check that. If I click F max, yep, that does look to be about 10 there. It overshoots it a little bit. Maybe you can trace it. So when x is equal to 1, we have, when x is equal to 1, y is equal to 10. When x is equal to 0, when x is equal to 0, y is equal to 4. So this is correct so far. You can type in the rest of them and double check it for yourself, but that is how you will check your final answer. And then, of course, you'll need to include a nice little graph. So that gives you a little insight into how to do this for the SAC. There are going to be other components, of course, but this is kind of like one of the key ideas in this SAC. So just like with the first one, there's kind of like a procedure that I'm teaching you here, and then part of the assessment, like I said, there'll be other questions, but part of the assessment is your ability to implement this algorithm, demonstrating your use of CAS calculator. So make sure you're explaining what you're doing at every step here. But yeah, to recap, in order to find the spline, you need to first find the linear equations that you could use to connect these points to one another, like we did here. Step 2, work out what the gradient at each of these endpoints for the spline will be, which will be the average of the gradient of the two lines that are adjacent to that point. And then step 3 is to just solve using your knowledge of simultaneous equations, define a cubic, sub in the points, sub in the gradients at those points, because you need 4 pieces of information in order to find the 4 variables in a cubic equation, and then that will give you each of the equations. And then finally, you need to define it using function notation, just like I did here, specifying the domain over which each of those equations are being applied. All right, so that's all for today, guys. I'll catch you guys soon. Have a nice weekend, and yeah, looking forward to seeing you on Monday.